Thank you for the introduction, and thanks, Aaron, for coming. So today I'm going to talk about my recent work with my advisor, Eric Stamber, regarding the exact steering bound for two-qubit Werner states. So in short, we are going to answer a question that has been there for a while regarding the role of POVMs in quantum steering. So I realize that quantum steering is not a well-recognized concept compared to the entanglement and nanocarrier, so I'm going to give a really light introduction for how they are related. So essentially, for all of this non-classical correlation that can be emerged from a distant lab scenario, you are just looking at different quantity, and essentially they are corresponding to different non-classical resources. For example, for entanglement, you are assuming that you can perform the full tomography over your system, and in the end, a state is entangled or not is based on whether it can admit a separable model or not. And by comparison, in a non-locality scenario, or sometimes people will call it a device-independent scenario, you don't fully trust your devices. So instead of looking at the state tomography result, you're looking directly at the kind of correlation that can be generated from any arbitrary measurement that you can perform. And if all the correlation, considering all different general measurements, can always be predicted by a local hidden variable model, then you say that your state is local and cannot be used for violating any Bayesian inequality. So there is a third definition of this kind of non-classical correlation in distant labs that is quantum steering, and it is basically a mixture of the other two. So we perform measurement on one side, on any side, and we look at the post-selected state on the other side. So if the post-selected state can always admitting the so-called local hidden state model, then we say that the state can be classically simulated in this scenario, and the state will not be useful for quantum steering. So a lot of discussion has been made along this direction, trying to understand their relation and their differences. But simply put, it has been shown that for all pure state, they are equivalent, but for general mixed state, they are strictly different concepts. And more specifically, there exists some entangled state that cannot be used for quantum steering, and there exists state that is useful for quantum steering, but is not useful for violating any Bayesian inequality. So the most typical example that people are usually looking at, actually maybe the best understood example, is this classes of two-qubit Werner state. And it is, in qubit case, the Werner state is written as a classical mixture of maximally entangled state and the maximally mixed state. So the most entangled state and the least entangled state. And what people have trying to figure out is at what critical value the state become entangled and at what value the state becomes steerable and non-local. But unfortunately, only a really incomplete knowledge has been known regarding this state. And what has been known so far is that, for example, I want to emphasize that in this talk, I will exclusively focus on the qubit Werner state, but just historically, the model that was built for Werner state is the first model that can be generalized for any other general state or higher dimensional states. So what has been known so far is that entanglement is easy. You can figure out the bound for entanglement at r equals 1/3 for this class of state. For non-locality, that's extremely difficult. And even when you consider a restricted family of measurement, the projective value to measure, it is not solved. And it turns out that the quantity that you want to solve, when the upper bound and lower bound coincide, that's corresponding to a universal constant known as Grothendieck constant. So there are a lot of story that has been going on regarding trying to get this number correctly, but this is only considering it's only considering a projective value measure at this moment. So the quantum steering problem seems to be a little bit more manageable because people already have an answer if we only consider projective value measure. And people know that the bound is at r equals 1/2 based on the construction of a model and also violations of some kind of inequality. But what is not known before is that we use POVM to do a little more, since the best model that we know so far is a model that tells us a state will be not steerable under POVM at 5/12, or 5/12 over here. And today we are going to fix the gap. So there is a unknown gap between 5/12 to 1/2, and we are going to fix the gap today. So this problem is actually asked by Werner himself, and also listed as an open problem in the past, and is asking whether we can get a critical value for deciding whether the Werner state becomes steerable or not. So, and today we are going to give the first answer to this question, and we are going to show that the bound for POVM is also at 1/2, and POVM is useless in the quantum steering scenario, at least in general. Okay, so a related concept. So people like quantum steering a lot because quantum steering is related to another interesting concept regarding measurement incompatibility. So there are a lot of one-to-one correspondence between these two concepts. So the problem that we just asked about the Werner's problem can just be phrased as an incompatibility problem that I will just introduce in 1 minute. And simply put, when we are looking at the Werner state quantum steering problem, we are trying to find a probability measure and a family of hidden state and some response function that is both positive and normalized in order to make the simulation for Werner state works. And a related concept called measurement incompatibility is defined as follows. So we want to making sure that a set of measurements, noisy one for sure, that can be simulated by one single measurement with some post-processing. So this can only be done in the noisy case because if R is equals to 1, for example, this set of measurement consists of those non-commuting one. So then those measurements can definitely not be simulated by any one single measurement. And we want to figure out at what critical value R we will have a simulation model that is of this form, consists of parent POVM and also response functions that is positive and normalized. So this is a so-called incompatibility problem. We want to determine the critical value over here, such that this set of noisy measurement becomes incompatible and becomes simulable by a joint measurement, by one single measurement and post-processing. So there are a lot of story about that, but just simply put, if you can find the local hidden state model, you can find the compatible model. So these two problems are actually equivalent. So I won't distinguish these two problems in the following discussion, but I will just use the notation for the compatibility problem just for simplicity. So they are equivalent if you consider POVM, and they are also equivalent if you consider POVM. So the bound should be worked for both of them. Okay, so there are one slice for motivation for why this is important. In quantum information science, the most general measurement that one can consider is a measurement consists of a set of positive operators that also satisfy the normalization condition. And the projective valued measure is just a special subset of those measurements that satisfied projection property as well. And the question that people usually ask a lot is, in what task can we use non-projective POVM to get some advantages over those projective ones? And it turns out that there are a lot of examples in quantum state tomography, in state discrimination, in metrology, in randomness generation, and in protocol, all those protocols using pretty good measurement. So those protocols all shows you that if you use a non-projective POVM, you can gain some advantage. But here we are asking a related, slightly different question that is regarding if there is a task that all PVMs, projective value measure, can be simulated classically, can we get some quantumness by using POVM? And at least in the quantum steering problem that we are going to share today, we don't have any advantage for POVM, and we are really interested in know whether this is more general or there are other examples that can show advantages with POVMs in this kind of simulation scenario. So the proof that I'm going to give today is quite constructive, so I will present most of the proof. But the important information that I want to deliver is that simulating a POVM in this kind of quantum steering scenario might not be too difficult, actually. It actually might be even simpler than simulating projective valued measure. So that's the kind of information that I want to convey. So let's start it with a simple example to help you to understand our construction of the local hidden state model. So this example is just taken directly from the first example, the Werner state model, but we just interpret that as a compatible model for simulating all projective valued measurement, noisy projective valued measurement. And for Qubit case, the classes of projective valued measurement can just be parameterized by like the R over here as the noisy level, and the direction M over here representing the direction of the projector. And it turns out that at R equals to 1/2, at this noisy level, the set of all projective valued measure can be simulated by using this parent POVM. So you have a lot of rank 1 effects that is even uniformly distributed over the Bloch sphere geometrically, and you use a response function that is a theta function, a step function, and you can show that these two elements can already help you to reproduce all different noisy spin measurement, and geometrically it looks as follows. And the problem that we want to ask is that can we actually construct a model that works not only for PVMs, but also for all noisy POVM at the same noise threshold? And again, in this geometrical representation for Qubit case, all the noisy POVM can be parameterized as follows, with some extra parameter that is representing the trace of the effects. And there are some non-trivial normalization conditions that you have to obey, and actually those non-trivial normalization conditions is important for us to tell whether our model is actually is actually well defined or not. So, but before that, there is a simplification that one can always do. That is based on the extremality of measurement. So for any d-dimensional quantum system, people know that the extremal POVM that you have to consider is with at most d-square outcome. So that means that in order to show that we can construct a compatible model for all noisy POVM, actually we only have to construct a model for all full outcome noisy POVM. That's sufficient. So if we can, and the main result that we are going to show is that a way to construct a local hidden state model or a compatible model for all full outcome POVM. And that's suffice, since those are the only extremal one, and all the other non-extremal one can be written down as a complex combination of those, and that can be simulated for free. So the proof idea is as follow. We want to move from the simulation for all projective valid measure to POVM. From PVMs to non-projective dichotomic measurement is simple, since none of those non-projective dichotomic measurement is extremal, so they can be simulated for free. And then we will attempt to simulate a 3-outcome measurement, the family of all 3-outcome measurement first, and then we will move from 3-outcome measurement simulation to a 4-outcome measurement simulation. So a naive way of doing this simulation for all 3-outcome measurements is as follows. We can, for example, we already know that we have a model that can help us to do the simulation for projective measurement. And each individual effects for any 3-outcome measurement will be proportional to the projective measurement. Then one can easily say that we can just modify the response function a little bit. We use the same parent, we use the same pi n for the simulation, and we modify the response function a little bit, taking that from a step function from 0 to 1 to a step function from 0 to 2 times UA. But this, of course, doesn't work, because if you combine the simulation of this form together with 3-outcome POVM, the normalization condition will not be satisfied. So you will have some of the response function being greater than 1, and some of them being less than 1. And that's exactly the thing that we want to fix. So we want to have some intuition to find a way such that we can make that renormalize, and that kind of response function can actually be used to do the simulation. And the intuition is actually also quite simple, based on the following 2 observations. The first observation is that we are using these families of parents, we are using these families of parents to do the simulation, but all of these parent effects, they are not linear independent. They are actually linear dependent. They are infinite many linear dependent relations over there that you can explore. And that means that the response function that you construct for the simulation earlier on is not necessarily unique. So you can use those linear dependent relations for the parents POVM to search different response function that gives you the same simulation. And the task we want to do is actually find those response function that is still useful for the simulation, but in this case being normalized. And the second observation is also crucial, because if you want to use the linear dependent relation for all pi n, there are infinite many of them, since this is the infinite many outcome measurement you are considering at first. So you have to search among a really big size of linear dependent relation to make that smooth. So a crucial step for making that happen is try to do some coarse graining over the parents POVM. We want to turn infinite many outcome parents POVM into a finite outcome one, and then we explore the linear dependent relation for those finite outcome POVM, and then applying those back to give us a response function that works in the original setting. And just as a quick example, what we did for 3-outcome POVM. So for a 3-outcome POVM, we want to simulate is just a POVM that consists of 3 different effects, parameters as following, and the normalization condition will give you some non-trivial constraint for those parameters that you defined for those effects. And the first step, find the coarse graining. I want to emphasize over here the coarse graining is not unique. You have a lot of different ways of for doing this coarse graining, and we are doing a coarse graining using the geometrical approach. Since before we have this hemisphere defined by each individual vectors corresponding to those effects. So taking those 3 hemispheres together, actually those 3 hemispheres divided the surface of a sphere into 6 disjoint regions. And we just assign the integration over those disjoint regions and call this as a coarse-grained POVM, which consists of only 6 effects. And the region is labeled as pi1, pi 2, pi 3, and their complementary part. And the original unnormalized response function that we construct earlier on can just be represented as follow, consists of just a 3 by 6 matrix. And the normalization that we want to fix is we want to make sure that the sum of each columns over here are actually equals to 1. Obviously, they are not equals to 1 at this moment, except for the trivial projective measurement case. So what we do is we want to explore all the linear dependent relation of those 6 coarse-grained effects. And it turns out that we can actually enumerate all the linear dependent relation based on the normalization condition and also the symmetric property of the dividings over here. And we can use these 2 linear dependent relation to adjust the values in the table. So originally the table is, each column of the table is not sum equals to 1, but after applying this linear dependent relation, we can actually make that equals to 1. And there's one caveat over here, that is, when you do the smoothing, when you apply those linear dependent relation to make them normalized, you have to be careful that you shouldn't have some value over here being negative, since you have to have a positive, you have to have a response function that is both positive and normalized. But it can be shown that it can always be done, and by using the property of the fact that this original parent, the original POEM that you want to simulate is normalized. So using this non-trivial constraint over here, you can in the end show that this simulation actually gives you a response function that is both positive and normalized. And another important thing that I want to mention over here is that if you notice, when I do this smoothing over here from this unnormalized response function to this normalized one, I don't actually have to adjust the response functions for simulating the first effects. So the first row over here is remaining unchanged. And this is actually crucial. This is actually crucial for us to moving from a 3-outcome simulation to a 4-outcome one. And the simulation works as follows. So I won't give all the I won't be able to give all the detail, but try to give some high level idea on how this works. So this works in a way that any 4-outcome POVM, we can again geometrically represent that as a tetrahedron, consists of 4 different vectors in the block sphere, and we can introduce 2 antiparallel vectors over here that can help us to form 2 different triangles in the block sphere representation. And then what we are going to do, the first step is we are going to construct some simulation model using the result that we just showed in the 3-outcome POVM case, and then we combine them, and that will give us a simulation model for the 4-outcome POVM. It is not trivial. It is only possible due to the fact that we observed earlier on that we can keep the response functions of simulating the first effects, the first row here, unchanged when we do the smoothing function. And here is a simple sketch. We define those 2 antiparallel vectors based on our understanding about the original vectors corresponding to the effects of the original POVM. And then based on that, we construct 2 3-outcome POVM over here. We can apply our model that we had for the 3-outcome simulation, and we can obtain a slightly more complicated model, but all this value over here can actually be analytically computed. But the important part over here is that when we do this smoothing, so both of these 2 tables, they are normalized. The response function over there are positive and normalized. And more importantly, when we do this smoothing, we actually haven't changed the response functions for those 2 pseudo effects that we introduced. So we don't have to adjust those. We only adjust the original effects coming from the original 4-outcome POVM. And then we combine them together. We define a different coarse graining. Actually, it is a fine graining of the previous coarse graining. So this coarse graining consists of 18 effects, and is defined by considering all these 6 vectors together, and that defines a disjoint region on the block sphere that has 16 different regions. And we combine those together, and the response function that we construct in the previous table can be inherited in this new table, consists of 18 columns over here. And we just remove the simulation for the 2 pseudo effects that we introduced for simplicity. Since those 2 has never been changed, they should still be summed to a constant. So the normalization for the original construction guarantee that the new table is still normalized, that each column over here should still be summed to 1. So we get, in the end, a model for simulating all noisy POVM with all the response function that is analytically computable. And the only thing you need to do is you need to understand what kind of measurement that you want to simulate. So with that, we complete the story. So we can simulate in 3-outcome POVM, we can simulate in 4-outcome POVM, and then we can actually simulate in any POVM at this noisy threshold. And that answers the question about both the noisy threshold for compatibility measurement and also the noisy threshold for simulating Werner state at r equals to 1/2. And few notes. This is actually quite important about uniqueness. I think I commented earlier on that simulating POVM is actually easier in some sense because you will figure out that the simulation, the response function for those simulation is only unique when you want to simulate a projective value measurement. For the simulation for all POVM, actually you have a continuous set of response functions that you can choose. So you can choose different response functions that can gives you the same simulation. So those simulations for POVM are actually not unique and actually in that sense easier. And all of our result over here is analytical. So all the response function, if you want, you can compute in them explicitly. And there is a parallel work that is coming out almost at the same time as our work, which gives a existence proof for this problem. They show that there always exists a compatible model that you can have at R equals 2.5, and using a completely different cost grading idea, and which also confirm that this kind of simulation is not unique. And the third point is that because quantum steering is a weaker concept of built on the carry. Actually, the bound that we just introduced today, R equals 2.5, is also the best bound for simulating local hidden variable model for Werner state for simulating local hidden variable model for Qubit Werner state. So the best known result before is R equals to 0.58. Okay, outlook. Our approach gives the best bound, the exact bound for simulating a quantum steering of Werner state, and also gives a better bound for simulating a local hidden variable model or a local model for Werner state. And we hope the idea of try to do cost grading and try to relocate the response function can help people to find a better local hidden state bound and also a local hidden variable bound. And another important idea that we are coming up with when we were doing this research, we figured out that actually the discussion of a finite model is also interesting, and there are a lot of actually non-trivial results that could emerge if we restrict our model to be only to be built with finite classical resources. So in the previous model, maybe you have noticed that all the simulation that we have considered consists of infinite many shear randomnesses. But if we restrict that, actually some interesting result can emerge. For example, we show that POVM and PVMs actually become inequivalent if we have a restriction on the amount of classical resources you can have in those simulations. So that ends my talk, and happy to take some questions.
Thanks a lot for the nice talk. Questions?
Thank you for the nice talk. I would like to clarify what is the simulation of the quantum measurement. What are the allowed operations when you talk about the simulation of quantum measurement? So,
can you repeat that again?
sorry. What are the allowed operations when you talk about the simulation of quantum measurement?
Oh, I see. The operation. The question about what is the operational definition for the simulation of quantum measurement?
Yes.
So I think I explained that really briefly, but the idea is that using this as an example over here. The idea of describing the simulation of a set of quantum measurement is actually trying to looking for one joint measurement to make sure that you can get all the statistics that you can observe for those set of measurements. So for example, in a scenario that you have a set of different MAX with X being the label of the measurement and A being the label of the outcome, then if this measurement become noisy by controlled by the noisy value over here, they can become compatible, meaning that you can find actually one single measurement, and you can send the state originally to the set of measurement with some classical instruction on what kind of measurement you choose from the set. You can actually do that in a different way. You can just perform one single measurement on the quantum particle, and then you take the classical value and apply a post-processing functions to obtain exactly the same statistics that you can obtain from the original setting. So in that sense, this one single measurement simulating all the correlation that you can generate from the original set of noisy measurements.
Thank you very much.
Hi, thank you for the talk. I think maybe you said it very quickly at the end, but I missed it. So for other 2-qubit states where we have local models for projective measurements, does your kind of idea work? You mentioned this T state maybe, but I was just wondering how, like, can we use this as a general method now for going from PVMs to POVMs?
Okay, the hope is that this can be a general method, but also there are difficulty. For T state, it's easy. is quite simple, since for t-state, you have a really geometrical representation for t-state. So for what you can have after you post-selected the state in the for t-state. So it is not a block sphere, but instead it's ellipsoid in 3 dimensions. So for that, you can actually, since if you notice that the way that we do the cross-graining in this example is quite geometrical-based approach. And for t-state, you still have that geometrical-based approach. And for general state, it is more difficult, but it's not surprising, because the exact value for those class of state, when they become steerable or not, under PVM is only numerically known. So there are no analytical expression for those. So, and, sorry, let me go to that slide quickly. So I said over here, quickly. Oh, okay. Yeah. So for t-state, you have geometrical interpretation of what happens in the quantum steering scenario. You can use those geometrical representation to find the corresponding cross-grain that you want to make this simulation happen. But for general state, the geometrical picture is still there, but it is actually in 4 dimensions, and it makes things much difficult. And it's not impossible, but just due to the fact that we don't know exact value for simulating all PVMs, then that makes it even more difficult for us to simulate all POVMs. But it is not impossible. It becomes much more non-trivial if you go from qubit representation to a higher dimensional representation, since you don't have the geometric picture. And we also notice actually quite few difficulty in making that generalization. And some of us is actually questioning the result. They actually believe maybe POVM could be more advantageous than PVMs in a higher dimensional system.
Thank you.
Okay, I think we have to wrap up, but let's thank the speaker again.